Hello all. In this video, we will be discussing about the lamina hygrothermal effects. Until now, we have been discussing the stress-strain relations in a lamina using the engineering constants. But we have always assumed that the environment is fixed, meaning the temperature, the humidity, these are not changing with time. But in practice we know the composite structures we design, they are serving in an environment where sometimes there are temperature changes as well as humidity changes. These temperature and humidity changes can bring in changes in temperature, stresses as well as strains. So we will now see how these temperature effects and the moisture effects can be incorporated in the stress strain relations. For this, we'll first start with what we have already discussed for 2D stress strain relations for a lamina. So, meaning that what is the relation between the stress and strain for a specially orthotropic lamina. So, these are the strain stress relations. The strain is related with the compliance matrix S times the stresses written in terms of the material coordinates. That is why we have this 1 2 written. Since we are looking in the material coordinates, that's why we mentioned that these are the relations for specially orthotropic material. Similarly, here we have the stress strain relations where the stresses in the material coordinates is given by the stiffness matrix Q times the strains in the material coordinates. Next, we also showed these relations in the body coordinates where we said the strains in the body coordinate xy is written in terms of the transformed compliance matrix S bar times the stresses. And for the stress strain relations, we use the transformed stiffness matrix with Q bar. And lastly, we also showed the transformation between stress from one coordinate system to the other, meaning going from body coordinates to the material coordinates, we use the transformation matrix T. So when we have stresses in the body coordinates, we pre-multiply it with the transformation matrix T to get the stresses in the material coordinates. 1. Similarly, we can do the same for strains. So let's say if we have strains in the material body coordinates xy, if we pre-multiply that with the transformation matrix, then we get these strains in the material coordinate system 1. So last time we emphasized saying that when we write the strains, we need to ensure that these are tensorial strains. That's when we can apply these transformation matrices. To ensure that, we have added this half for the shear strains both in the material and in the body coordinate system. So these are the relations we have for uh, where the environmental conditions are not changing, meaning the temperature and the humidity, let's say, are fixed. But we will start to see now if these changes occur, the environment changes occur, how it affects the stress and strain as well as their relation. So we'll start with temperature changes. So when we have temperature changes, it induces some thermal effects into the material. One thing we can expect is with increase in temperature, the dimensions increase. Or if the temperature is decreased, the dimensions might decrease. So either there is a stretch or compression in the material. Similarly, when it is exposed to humid environments, like what happens, let's say we have a composite structure which is passing through a humid environment, then it absorbs the moisture from the environment and then there is some swelling happening. So because of this swelling, there is an increase in the volume of the material. So it's not always true that all composites have this swelling, because there are some composites where with increase in temperature or humidity, there might be a decrease in the size of the component. So which means they have the negative effect. But when we are discussing about the moisture changes, we say that it induces hygroscopic effects. Hygroscopic meaning the water molecule related effects. But then we have been only looking at this temperature and moisture independently. But what if there is a both a temperature change as well as a humidity change? That's when we have the hygrothermal effects. Hygrothermal meaning both humidity effects as well as the thermal effects. So that's exactly what we'll be discussing in this video to see how these hygrothermal effects affect the stress strain relations. So before we go to the start discussing with orthotropic material, let's look at how temperature affects, let's say, the isotropic materials like aluminum and steel. So in isothermal materials, we are familiar with this concept of CT, meaning coefficient of thermal expansion. What does it mean for uh, unit change in temperature? What is the unit change in the strain in the material? So how do we represent? So let's say epsilon I is the change in the strain in the ith direction. This is given as alpha delta T, where alpha is the coefficient of thermal expansion and delta T is the temperature change. So let's say delta T can be written as T minus T naught, where T is the final temperature and let's say T naught is the temperature where the strains are zero, initial temperature. So in isotropic materials, we know that the properties are independent of the direction. What does it mean? It means that the coefficient of thermal expansion in the direction x as well as y and z, in all three directions, we have the same alpha value or the coefficient of thermal expansion. That is why there is no need to represent this alpha with a subscript like I, meaning that alpha 1, alpha 2, alpha 3 or alpha x, y and z, all three are the same. So we can simply write it as alpha and that should suffice. But another important point is what happens when there is a temperature change? Do we see only the normal strains or do we expect to see the shear strains? The answer is we only expect the normal strains to change, meaning uh, strains in the x, y, and z directions will be increasing. But if we consider the shear strains, all those components go to zero, meaning there is no distortion in shape of the unit infinitesimal cube we are talking about, but there is only change in the size of it. So we can write it as alpha I is equal to alpha times delta t, where I equals 1, 2 and 3, but equals to 0 when I equals 4, 5 and 6. What are these subscripts 1, 2, 3, 4, 5, 6? These are the contracted notations we discussed few lectures back. So let's say this is the strain vector in 3D. This can be represented, we said, as epsilon 1, epsilon 2, epsilon 3, 4, 5 and 6. And we also mentioned the first three are the normal strains. So these are epsilon 1 1, epsilon 2 2, epsilon 3 3. But the last three are the shear strains, which are these epsilon 2 3, epsilon 3 1, and epsilon 1. So we are saying that in the case of an isotropic material, the shear strains go to 0. But the normal strains are the ones which are non-zero. Okay, with this background of the isotropic material, let's see for orthotropic material how we can extend these concepts. So now we'll start looking at these hygrothermal strains for the orthotropic material or the lamina. We'll start with the thermal effects. And let me repeat that we are looking this for an orthotropic material, meaning that the properties are different in the mutually perpendicular directions. So along the fibers, we expect the coefficient of thermal expansion to be different from the transverse direction because we know that the fibers and the matrix are two different materials. So along the fibers, it will be dominated by the fibers, but transverse to the fiber material, the matrix also plays a role. So for that reason, let's say if we are looking at now, if we look at the strain because of thermal effects, we'll write it with a superscript T. This is given as alpha I times delta T, where I goes from 1 to 3. So if you notice, the change we made from isotropic materials is instead of writing it as alpha, now we represent it as alpha I, meaning your alpha 1, alpha 2 and alpha 3 values are different. And mind you, the we are currently looking at specially orthotropic materials, meaning these directions 1, 2 and 3 correspond to the principal directions or the material coordinate systems. Okay. And for I going from 4 to 6, this value is 0. So we are saying that in the specially orthotropic material, there is no extension shear coupling, meaning that there are only normal strains. We don't expect to see shear strains. Okay. So, and these definitions are alpha i's are the coefficient of thermal expansion. Okay. Now let's move to the moisture effects. So here too, we are saying that when there is a change in the moisture concentration within the composite, it can either increase or decrease in the size, or there can be expansion or contraction. So that will represent using the epsilon m with a superscript m, meaning for the moisture effects is given as beta I times C. Here I need to say this is for I goes from 1, 2 and 3, and C is the concentration, moisture concentration. Again we can see that there is a subscript I, meaning that your beta I or the coefficient of hygroscopic expansion in the direction 1 is can be different from beta 2, which is the coefficient of hygroscopic expansion in the perpendicular direction, perpendicular to the fibers. But let's say if you are talking about a transversely isotropic material, then we can say your beta 2 and beta 3 could be same. But this happens, as we are mentioning, is for a transversely isotropic material. according to the definition of these transversely isotropic materials, we said there is a plane existing where the properties on any direction in that plane are the same. So here that plane is 2 3. 2 3 is the plane where we are saying the properties are the same in any direction. So we can take beta 2 is equal to beta 3, but of course, not all composites have to fall in this category of transversely isotropic material. So we can also have materials where all these three, beta 1, beta 2, and beta 3, are unequal. And when we say C for the moisture concentration, here we are assuming that at moisture concentration of 0, the corresponding strains are also 0. Here we only mention the strains in these directions 1, 2, and 3, but these strains are 0 when I equals 4, 5, or 6. Okay. So mind you, what we are looking at here is the linear contribution, which happens only in a narrow range of temperature. So these linear relations for thermal effects as well as the moisture effects only happens at a narrow range of temperatures, or the narrow range of moisture, or the water concentrations. But if the ranges are large, it could also be non-linear, and the analysis gets a little more complicated. But at least for this course, we are only focusing on these linear relations for the hygrothermal strains. We have looked at the individual effects of temperature and humidity, but if we have both, so which means hygroscopic strain, since we are looking at a linear elastic material, we can do the superposition, meaning the total strain because of the hygroscopic effects is the summation of strains coming from the temperature effects plus the strains coming from the moisture effects. So which can be written as alpha I delta T plus beta I times C when I equals to 1, 2, and 3, and is equal to 0 when I equals to 4, 5, and 6. Okay. This should summarize how we look into the effects of these hygrothermal effects on the strain. So we are using these linear relations, using this alpha I times delta T should bringing the thermal effects on strain, and the beta I times C should give the moisture effects on the strain. And we said because we are looking at a linear elastic where superposition is possible, for the hygroscopic effects we simply added the temperature effects and the moisture effects. Next we move on and see how we can use these strains to now define the stress strain relations. Now if you are looking at the total strain, we should also include the mechanical strain induced plus the temperature effect strain and the strain coming from the moisture effects. Now let's write all the components in the material coordinates. So let's say we are looking at epsilon 1, epsilon 2, and gamma x 1, 2. And we'll start by rewriting the strains for the mechanical contribution. This will write it as a product of the compliance matrix times the stresses. So the compliance matrix, if you recall, is written in terms of S11, S12. Since we are talking about especially orthotropic, there is no extension shear coupling, so it goes to 0, S22, 0 again, S66 times the stresses, which are sigma 1, sigma 2, and tau 1, 2, plus the strains because of the temperature, we'll write it as alpha times delta T, but now we'll write it in terms of alpha 1, alpha 2 and 0. So because 1 and 2 are the two directions of the plane, and the third component is the shear component. For a shear specially orthotropic, we said the shear is 0. So that's why the third component is 0 times delta T. Plus for the moisture contribution of strain, we'll write it in terms of beta I. So it will be beta 1, beta 2, 0 times C. Sure. So this should give a complete expression for the total strain. Okay. So now we will again write it in short, so that now we will try to use this expression to bring in the how do we write the stresses in the specially orthotropic lamina. Now let's rewrite this expression in a short notation, saying that these are the total strains is equal to S matrix times the stresses plus alpha vector times delta T alpha I plus beta times C. So from this we can also write the corresponding stresses. So for me to write the stresses, I should write it as S inverse times strain, total strain minus alpha delta T and beta C. Okay. So this should give the stress strain relations or the strain stress relations for specially orthotropic lamina under hygrothermal loadings. But now let's see, uh, we already know from our understanding of strength of materials that, let's say this is an isotropic material and I increase the temperature, there will be a corresponding increase in strain. So it will change the dimensions and introduce strains. But will this specimen introduce any stresses or not? That depends on whether it is constrained or not. If I restrict the expansion, that's when we increase the stresses. But let's say if it is free to expand, then there are no stresses build up in the material. So now let's look at both of these conditions separately and see what is the implication of these equations we just derived. So we'll start with unrestrained. So in unrestrained we say the stresses go to 0, meaning sigma equals 0. So let's plug in into this equation. Let's say this is equation 1. So once we plug in into that equation 1, I can rewrite it as strain epsilon is simply alpha delta T plus beta times C, right? So here we can see that the expression is much simpler because the stresses have gone to 0. But now let's look at the second possibility where it is restrained. So what we are calling looking at is a completely restrained, meaning that we are not letting the dimensions to change. Ineffectively, what we are saying is the strains are 0. So if I plug in this into again equation 1, it should give null vector is S times the compliance matrix times the stresses plus alpha delta T plus beta C. And if I now write it in terms of stresses, it should be S inverse times minus alpha delta T minus beta C. But we know that the inverse of the compliance matrix is the stiffness matrix Q. So we can rewrite this as Q times again minus alpha delta T minus beta C, which is the stresses which occur because of these constraint we have applied. So this should give us an idea about how to write the stress strain relations when there are hygrothermal loads also involved. So here we have only looked it at the lamina. Later when we discuss about the laminate where it is a stacking of these laminas, we will also see how these equations can be taken to write the mechanics of the laminate under hygrothermal loads. Until now, we have been looking at the specially orthotropic where there is no shear strain involved. But now let's look at generally orthotropic materials, which means it is at an angle to the principal coordinates. So in this direction, now we will start to see the shear strains. So now let's see how can we represent the shear strains, epsilon x, epsilon y, and gamma xy. So we have written these strains in the body coordinates x and y. So previously we said it is a total of the mechanical strain plus thermal effect strain plus moisture effect strain. So we'll write in the same fashion, but previously we wrote it in terms of the compliance matrix times the stresses will give you the mechanical strain. But this time we should write it in terms of the transform compliance matrix, which are S11 bar, S12 bar, and S16 bar. Earlier, this S16 was 0 because it's especially orthotropic, but now that we are looking at a generally orthotropic, these are no more 0. We do have this extension shear coupling. So S22 bar, 26 bar, and S66 bar times the stresses in the body coordinates sigma x, sigma y, tau xy plus now we are writing the strains because of the change in temperature. So we'll write it as alpha times delta T. But the way we write alpha is it will be alpha x, meaning the CTE in the x direction, alpha y, and alpha xy times delta T. Similarly, strains from the moisture we'll write it as beta x, beta y, and beta xy times C. But here I need to mention how do we get these alpha in the body coordinate system, meaning alpha x, alpha y, and alpha xy. How do we get it? We get it from using the transformation matrix where we started with alpha 1, alpha 2, and 0. But since we are using a transformation matrix, here we are going from the materials to the body coordinates. So we should be using the inverse transformation matrix. And then since this transformation matrix can only be applied for tensorial quantities, we should write these as by 2. So the alpha xy by 2 will bring it from the engineering CTE to the tensorial CTE. And the same thing applies for the CHE or the coefficient of hygroscopic expansion, where we write it as beta x, beta y, and beta xy by 2 is given in terms of inverse transformation matrix times these beta values, beta 1, beta 2, 0. So this stress strain relation should help us to find the stresses and strains where a combination of mechanical loads, thermal loads, as well as the hygroscopic loads are involved. So with this, let's summarize what we have discussed in this video. We said that when the environment is changing, where there are changes in temperature or the changes in the humidity, that brings in an effect on the stresses and strains. So if it is only temperature changes, we said it is thermal effects, but if there is only moisture changes, we said those are hygroscopic effects. But if we have both temperature as well as humidity changing, that's when we call it as the hygrothermal effect. And later we also showed how these effects bring in changes in the strain. So we said alpha delta T will bring in the changes in the strain because of temperature change, and beta C will bring in changes in strain because of change in moisture. And for isotropic materials, we could have simply written it as alpha and beta without a subscript because the properties are same in all directions. But since we are looking at orthotropic materials where the properties change with direction, we should write it with a subscript alpha I and beta I. Later we showed uh, since we are dealing with the linear elastic materials, we can add up the strains. So the total strain is the mechanical strain plus the strain from thermal effects plus strain from moisture effects. And once we bring in the replace the mechanical strain with the compliance times the stresses, we get the stress strain relations, which includes the hygrothermal effects. And lastly, we said we can also extend the same derivation to generally orthotropic materials. The only difference we have done is we have replaced the compliance matrix with the transformed compliance matrix, and we also have taken care that the CTEs and CHEs are now written in terms of the body coordinate system XY. So with this, we'll conclude this video, and in the next video, we'll look at the failure of the lamina.